I think I'm probably the last generation that's ever had that. The slide rule was replaced by the Hewlett-Packard calculator about 10 years into my profession.
Gotcha.
The slide rule went the way of the passenger pigeon. As I go through this, I'm seeing that a lot of what we're doing today, and I think what you might see in your profession is as we're going through more and more of this, we analyzed with a book all this work and work on the Seattle freeway, work on the Minneapolis freeway system was all done out of this book.
Really?
This same book is the same total design book is now three AASHTO manuals.
Oh, wow.
So it's very much more complex and much more computer.
Yeah.
And what I've emphasized with them is that I think that it's important that you know some of the old methods because a little bit of the intuition about engineering is being lost. It gets more scary for you young people when it's so complex and it's so specialized. Yeah. And I don't think that that's what has to happen. I think basically there can be a little bit of meld between the two.
Yeah, for sure.
The system wasn't broke, but I rather than fight the new system, I'm just saying, pay attention to the intuition that you're learning in engineering.
Oh yeah.
And don't get lost in the complexities or the dependence on the computer.
Definitely.
Just makes you less and less conversant with engineering all the time. My concern today is that intuition is dropping off the screen a little bit, and I actually think it's best for every engineer to be able to design from the ground up, and that intuition is being set back a little bit in my view. But other things, quality of the quality of the student, and the quality of the student engineer that comes to us is excellent nowadays. It's just super. But they don't have the intuition, and I think that's important, so they need to keep their ear open.
In this module, we will explore structural design software focusing on finite element analysis. This type of software makes it possible for engineers to quickly analyze complex problems and rapidly design members. It has revolutionized the way we design structures. However, software use comes with the challenge of ensuring the validity of the analysis and design. This can be managed, but not without intention.
Finite element analysis is a numerical technique that breaks down the structure into small pieces and then mathematically treats each of the pieces and how they interact with each other, and then puts it all together at the end with a solution for what the forces and stresses are in the members.
The finite element method can be used for structural analysis, heat transfer, fluid flow, mass transport, and electromagnetic potential. In structural analysis, we use finite elements to determine displacements based on applied loading and stiffness. With displacement, we can solve for internal member forces and stresses. These can then be used to make design and evaluation decisions. Finite element analysis starts with nodes, which can displace in 3 directions and rotate about 3 axes. We connect these nodes with either line, shell, or solid elements. Linking 2 nodes generates a line element, which has 12 degrees of freedom, 6 translational and 6 rotational. Linking multiple elements permits us to create structural models and understand how loads, stiffness, and displacements of the elements relate. It doesn't take many elements to generate a tremendous number of degrees of freedom. Hence, finite element analysis developed alongside the computer. The fundamental relationship in FEA is force equals stiffness times displacement, exactly like spring theory. Expanding this to multiple dimensions and any number of degrees of freedom, we can write this equation in matrix form. We do this for either one element or an entire system. The stiffness matrix is a function of length and material and geometric stiffness. Modulus of elasticity represents material stiffness for linear systems. Area provides stiffness for axial and shear actions, and moment of inertia provides bending geometric stiffness. Putting this together for a single beam element in 2 dimensions, we get the following relationship. The hat on the force and displacement vector indicates the element local axes. One can begin to imagine how large this matrix gets for an entire structure. With a solution for displacement, we need a relationship to convert this to strain. For linear systems, we can use this equation. We then can convert strain to stress using the mechanics of materials relationship. If we prefer, we can utilize the stiffness matrix and displacements to solve for the forces and moments in each element. We can then use these to design or evaluate the members. The accuracy of a finite element solution increases as the model refinement or degrees of freedom increase. However, as we see in this chart, at some point increases in accuracy plateau, even with increasing degrees of freedom. It is therefore helpful for an engineer to balance accuracy with computational effort. One way to test this is to increase the number of degrees of freedom in the model and assess how much the results change. Fundamental steps in utilizing finite element analysis software include configuring the structure, choosing the appropriate level of refinement, 2D or 3D, assembling the model, loading the model, analyzing the model and designing members, validating the model and results, and extracting usable results. The Federal Highway Administration Manual for Refined Analysis in Bridge Design and Evaluation is an excellent resource for understanding what is known as refined analyses in the AASHTO LRFD Bridge Design Specification. A first step in creating a finite element model is configuring the structure. It is wise to start this step with sketches showing general concepts of what you want to accomplish. At this point, be creative and open-minded. Know that you will get to a final design, just not in one step.
So you can analyze the trusses in 2D by taking one truss panel and drawing it on a sheet of paper in an elevation view and solving for all the forces. In reality, the truss is a 3D space structure. And so you really have two of those panels and then connecting members in between. And so a true 3D analysis would analyze those two truss panels and all of the pieces in between using a finite element or a technique such as that. Well, the 2D method, a designer would like to use it because it's rapid, it's quick, and they could get to what they need to know pretty efficiently.
Assembling the model consists of node creation, connecting nodes with elements, setting boundary conditions, and assigning sections and materials. A model can be assembled from scratch within the finite element software or imported from a CAD program. The latter often allows easier creation of complex geometries. This model utilizes RAM Elements, a commonly used finite element program in the structural engineering industry. However, these steps apply to many structural design software packages made by a range of companies. We create nodes by inputting coordinates. Here's our first node. Let's copy the first node 171 feet in the x direction. This is the total length of the truss we are modeling. Here's the copied node. Complex structural models can have hundreds of elements, so it's critical to learn how to create them efficiently. Using the linear generation tool, we can quickly fill this space. First, select two nodes. We'll place 8 equally spaced nodes here. We've now created all the nodes for the bottom chord of our truss. The software sequentially numbers each element as it's created. We can turn on the nodal coordinates under View, Properties, to see the three-dimensional position of any node. Let's also turn on node numbering. Information only shows for selected elements, which turn blue. We create line elements by selecting two nodes, right-clicking and selecting Connect Nodes with Members. We can also select an even number of nodes and choose Alternately Connect Nodes with Members. This works well for similar types of members and speeds up the modeling process. There are many modeling tools you can learn to quickly create elements. Continuing this process, we can create every member in the model. Utilizing shells, let's create the abutment of the original Van Buren Bridge. I've already laid out the nodes at the corners of the abutment. Selecting the nodes in clockwise or counterclockwise order, right-click and choose Create Shell. To get understandable results, we need to align the shell axes in the same direction. It can also help to align the local axes with the model axes when possible. We can do this by selecting the shell and using the rotation angle in the spreadsheet or using the tools along the top of the window. The software will subdivide the elements when we select View Finite Elements. we can determine the maximum difference between nodes to control the mesh refinement. If we want to control the mesh more, we can physically subdivide the shell by clicking on Shells, Nodes, Segment Shells. We can select how many segments we want in each direction. With members and shells created, we need to assign boundary conditions. This tells the members how to interact with the world and one another. Any place a node touches the Earth, we apply a global boundary restraint. Recalling each node has 6 degrees of freedom, 3 translational and 3 rotational, we can constrain a node based on how it will be connected in reality. In 2 dimensions, we can relate common connections to resulting analytical restraints. We see the roller resists vertical forces only, while the pin resists both vertical and horizontal force. The moment connection resists translation like a pin, but also restricts rotation. These can be extrapolated to the 3-dimensional case. For the truss, it is pin connected on one end and roller connected on the other. This models reality and supports the truss vertically, keeps it from sliding horizontally, perpendicular to the span, and permits one end to slip for thermal expansion. Starting with the left support node, we go to the restraints group of the node spreadsheet and select Pinned. Notice the graphical representation of the node being restrained in translation in the X, Y, and Z axes. Now select the right end support node and choose Roller in X. Notice how this node is now free to translate in the X direction. For line member-to-member interactions, we can similarly assign 6 degrees of freedom to each end. For truss members like those in the historic Van Buren Bridge, the members behave more as pins than fixed connections. Hence, we will release moment resistance at each end. We do this by selecting all the members, then under the Members tab and Hinges group, select Hinge both ends. This means the software will treat each joint as a pinned connection. We can fine-tune member end releases by double-clicking the checkboxes in the spreadsheet. Keep in mind, if all members are pinned at a joint, we will get an instability. We can solve this issue by making sure one member at each node is not released. After creating line elements, we next assign their section and material. Select one or more members and navigate to the Sections group of the spreadsheet. If we want to use hollow structural sections, we navigate to the HSS table and choose a member section. Next, we go to the Materials group and assign a material. Hollow structural section is typically made of A500 grade C steel. In the View tab, we can toggle on member properties such as section and material. For shells, we assign material, shell thickness, and reinforcing cover. Material is the third icon over under shells. We select the material by double-clicking the item we want. Note, C360 means 3000 psi concrete with 60 ksi rebar. We can assign the mechanical cover for concrete in this tab as well. We assign shell thickness by selecting the second icon over and type in the thickness we want. With the model now configured, we are ready to apply loading. It is most effective to apply the loads unfactored, just as they are calculated from the code. This provides simplicity and flexibility when assigning load combinations. We first create individual load cases corresponding to the load types we have on this project. For now, let's create dead components and dead wear. To assign point loads for dead wear, choose it in the Conditions dropdown. Select the nodes where we want to apply this force and go to the Nodes, Forces, and Moments spreadsheet. Type negative 6.08 kips for the force in Y. Remember that we found these forces in Module 3. To assign line loads, follow the same process. Select the members and choose Members, Loads on Members. Click towards negative Y to assign a uniform downward force along the member length. We do this for each load case in every portion of the model. We next need to tell the software how to combine these loads. Opening the Add Edit tool in Load Conditions, we see that here we can define load cases and load combinations. Utilizing the AASHTO load combinations, we create a load combination for each case and enter the load factor in the combinations portion of the spreadsheet. We can select any load combination in the conditions list to view each load that will be applied. Now we run the model solver. In the Condition tab, select which load condition to include in our analysis. In the FEM tab, we can choose to segment members and shells. We usually don't change anything in the Solver tab, but can as needed. The Model DOF tab allows us to assign how many degrees of freedom to analyze. We'll leave automatic detection selected. When analyzing a planar truss, the software will automatically decide that a 2D analysis should be performed. Depending on the complexity of the model, the analysis may take seconds to hours or even days. The software completes the analysis of our truss in about a second. With the analytical results, we can now utilize the software to perform the appropriate code checks. We can choose which steel, reinforced concrete, and wood codes to check our members. After the design module runs, the software will show us if our members pass the code checks and other results, like stress ratio. We can also see detailed code check results by clicking Output, Design, Steel. We can now extract analytical results such as nodal and member displacements, member forces, shell forces or stresses, and modes of vibration. This can provide information for substructure design, connection sizing, how far elements move, and insight into the dynamic behavior of the structure. Let's walk through how to display these analytical results. We'll use the options in the View tab. To see the calculated support reactions, select both support nodes. In the View tab, toggle on Reactions. Select nodes and toggle on Nodal Displacement to see how far nodes move under load. To see internal member forces, select Members and choose Member Forces. We can choose to display axial force, shear, torsional moment, and flexural moment. We can also generate reports that tabulate these results. In the Output tab under Analysis, we find Analysis Results. Here we can generate various reports for nodes, members, and shells. It's very helpful to generate an envelope report, which shows maximum and minimum forces and which load combination caused that force.
Validating the results of finite element analyses, this goes back to that engineering judgment issue. They really need to understand all of the boundary conditions in the model and the loadings and have an idea of some of the places where they can test what the model did and see if it's reasonable or not. Sometimes they might look at a deflected shape, for instance, and see it doing something weird and then go back and find an error.
It is now critical to validate the model results. A simple mistake can yield useless results. There are a number of ways to do this, and include comparing model results to exact or approximate equation-based solutions, observe the deflected shape and decide if it is logical. For a load case, add all the loads in one direction and see if they equal the sum of the reactions in the same direction. Start with a more simple model and compare the results of a more developed model against it. For the truss model, we can compare the exact method of joints or method of sections to the FEA results. After analyzing our truss, let's select a few members and toggle on axial forces. Positive values represent tension, negative represents compression. Comparing these values to our method of joints from Module 4, we get the same values. Let's also check the reactions against our hand calculations. These match our Module 4 work as well. This gives us confidence in our truss model and the resulting analysis.
Challenges with FEA software would include some of them are formulated differently than others, and so there may be some better accuracy or precision in some than others. The biggest one, though, is the user. The user has to know has to have a feel for whether it's producing reasonable results or not. I guess you could call that engineering judgment, probably, but that is vital in using finite element. Otherwise, it turns into a black box, and you really don't have something you can rely upon. The thing is, it's so complicated. You're talking about a model with tens of thousands of elements. He may be right. I fear sometimes that he is. But then I also see some really brilliant young folks come out of college who are over it and who get it. And so that gives me hope.